Oh, yes, wonderful. Thank you, Sarahi. Sarahi, right?
Sarai.
What did it say it again?
Sarai.
Sara.
Sarai.
Sarai. Did I say it? Sarai. Okay, Sarai. Yeah, H is silent. Thank you.
No.
All right, well, folks, it's 11:03. That was 3 minutes, and it's basically silent in here. So I think we can go ahead and get started. Let's start with that first one. Now, this is my practice to know your names, and even if your name changes out, I'm now on the wrong end of the room. So I'm going to try to know your names. So first of all, what does f of x represent? Alexis?
The y coordinate of height.
Wonderful. The y coordinate and the height. That's a nice, long, perfect definition. So here's my graph of f of x, whatever your f of x might be. And then the f of x is the y coordinate, which, when we talk about the y coordinate, of course, we're looking at the y-axis, and it's the actual height of how far that is off the x-axis. So everybody in your chair, can you like rotate to look back this way? Because class will essentially be back here. I know your chairs are facing that way, but you should more or less be facing, the center of the room. That way you can look both ways either way. Okay, so thank you, Alexis. F of x is the height. What is an f prime of x? I don't see your name. Wait. What is it again?
Brandon.
Brandon. Okay, Brandon, please tell us, what is f prime of x?
Would be the slope.
Perfect. F prime of x is the slope. So I'm going to choose this point at the top, because at the top I know that f prime of x is equal to, what's the slope at the very top? 0, because it's a flat spot. So there's f prime of x equals 0. So there's the slope. And then what does the integral of f of x represent? Julian, that's right. Thank you, Julian.
The integral or area.
Yeah, the area underneath. So I'm going to go ahead and say the integral from a to b of f of x is going to tell us the area between a and b underneath the function. So that would be that area right there. So that is going to tell us the area. These are our 3 key ideas for the whole semester. We're not going to be doing integrals until October or November. But in any case, those are the 3 main ideas. What is the verbal definition of slope? David? How would you define slope in English?
Rise over run.
Rise over run is perfectly fine, although I hate that definition. Sorry, hate's a strong word. There's a better definition, which is the up, down, over the what?
Left, right.
Over the left, right. Very good. So up, down, over the left, right. So that's how we talk about slope. It is literally how is the function moving up or down, and how is it moving left or right. Okay, what is the meaning of the slope on a distance versus time graph? We just looked at one example of this. If you're looking at a distance versus time graph, like that picture of us going away from home towards home, what's the slope of a distance versus time graph represent? So M is telling you what? Bata? Okay, I'll call back on you for something else. Anyone want to share? What was the slope on a distance versus time graph? Yes? What is it? Yeah, the velocity. And we can all remind ourselves of that because according to the verbal definition of slope, which David just told us, the up-down is distance And then the right left is time. And anytime you have a distance divided by a time, such as miles per hour in your vehicle, miles per hour represents your speed. So the slope of a distance versus time graph is your velocity or your speed. Okay, what is the difference between a secant line and a tangent line? So here's a graph. How would I draw a secant line? Jacob?
2 points.
It has to cut through 2 points. So there is a secant line. A secant line cuts through 2 points. Yep, that's a secant line. How do I draw a tangent line, Simo?
There's a point on a graph. Isn't it like something like diagonal?
It just touches the graph at 1 point. Yeah, so it doesn't go through 2 points, it only cuts through 1 point. That's a tangent line. Okay, so building off of that, what's the difference between average rate of change and instantaneous rate of change? Which is which? Which one is the average rate of change? Efren?
The average rate of change is
This is the tangent, and this is the secant. Which one is the average rate of change?
the secant is your average rate of change.
Yeah, the secant is your average rate of change. You have 2 points, and it's telling you the velocity or the rate of change over that whole interval. Okay, and which one is the instantaneous rate of change? Oh, Allison? Yeah, the tangent one. That's telling you your velocity exactly there. Now, let's give an example of that. In your car, what does your speedometer show you? What is your speedometer showing you in your car? Instantaneous rate of change or average rate of change? Instantaneous, right? That's your speedometer in your car. It's telling you how fast you're going right now. So like if you're in your car and you're driving and the needle is pointing at 50 miles per hour, that's how fast you're going right that second. Right now your speed is 50 miles per hour and that's your instantaneous rate of change. Wouldn't it be interesting if your car also showed you your average rate of change over your whole trip? So like let's say you leave for work in the morning and then you get to work and then you can look back at your special average speedometer and it tells you your average velocity over the whole trip. And then with all the stoplights and traffic, you'd say, geez, on average, I was really only going 30 miles per hour because on average I had to stop at stoplights and then there was traffic and so on. Okay, well that's it. Those are my warm-up questions. So good morning, everybody. Let's talk shop a little bit before we keep going. Today is August 27th, right? So we're scheduled to do section 2.2 today. We have a couple problems to finish from 2.1, and then we'll do section 2.2. Did everyone sign in and pick up the packet for 2.2? I'm assuming? Okay, and then we have school on Wednesday, but then next week note that we don't have school on Monday. Even though we don't have school on Monday, do you still have homework due?
Yes.
Yes, you still have 2.1 and 2.2. So the homework from 2.1 is not due today because we didn't finish it. I'm extending it by a full week. So next Monday, you have to finish the homework for 2.1 and 2.2. Okay, would anyone like to ask any questions about the More website before we get started? First of all, I want to say that I did receive probably like 5 emails from you folks. That was really exciting. I would have preferred 20 emails, you know, to hear from all of you, like if you had any questions, but I was pretty satisfied getting 5 emails from you folks. So does anyone want to ask a question about the More website before we start? We were on section 2.1. I'll clarify something. Within 2.1, here was the assignment. There were 9 problems. And just to remind you, those 9 problems are the same 9 problems that you have on your packets from 2.1. All I did was print out these problems. And that's what we're doing in class. And then when you go home, you'll have the notes from class to do these problems. So for instance, so far, I would have hoped that you would have already done number 1, that you would have already done number 2. You would have, nope, we haven't done number 3 yet. So you no need to have done number 3 yet because we didn't do it in class. You could have already done number 4 because we did a problem like that in class. Whereas I think 5 we haven't done yet, 6 we haven't done yet, 7, 8, 9 we haven't done yet. So there were only a couple problems from 2.1 that you could have done. And I hope you didn't beat yourself up if you couldn't do the other ones because we haven't done it yet. But we're about to do them right now. Okay, does anyone have a question about this before we start?
But specifically the question about how to do part number 2.
Thank you, Allison. Number 2 right here? Okay, perfect. So what's your question?
It's on the second one, just because we didn't even do that one in class. But what
What's the average rate of change from 99 to 2001?
Yes.
Yeah.
So would you just do 1 minus 99?
1 minus 99. Oh,
Because it's O.
that's a good question. No, it's 2001 minus 1999. The question is, how many years difference is that? You can tell me this off the top of your head. How many years passed from 99 to 2001? 2 years, right? Because you went from 99 to 2000 to 2001. So whether you think of it as 01 minus 99 or 2001 minus 1999, the key question is how many years went by? And so 2 years went by. So for this particular problem, the change in the number of jobs was from, and watch this folks, I can actually type the slope formula into the answer and it should give me full credit. So the difference in the number of jobs, which is my y2 minus y1, is 770 minus 720. And then divide by the difference in the number of years, which is just 2 years. And so without even computing that, I'm going to hit submit. Oh, I didn't answer the other part. Hold on, let me answer this one. So also from 99, so that's 720 minus 625, also divided by 2 years. And let's just see. Boom, it gave me full credit, and I didn't even simplify it. But it knew I knew what I was doing. And so if I did go ahead and finish computing that, I would actually have the rate of change. Elsa, does that answer your question?
Yes.
Okay, great. Thank you. Good question. Yes.
I don't have a packet for 200.
Great. Thank you for saying that. Who else needs a packet from 2-1? Because I think I have some extras. But yeah, you're right. Wait. Sarahi. Sarai. Sarai. No. There's no H. Say it again.
Sarai.
Sarai. Sarai. Okay. Does anyone else need one besides Sarai? Okay. All right.
Do you have a sheet of paper when on my first day of class and you wrote that stuff?
Yes, I do. Let me give it to you after class. Yeah, you can get it. Okay. Well then, folks, let's go ahead and get started. We'll finish up 2-1. I do need to start with a joke. Remember, all of my jokes are funny. So here's the first one. When did the man go to the dentist? At 2:30. 2:30. All right. So let's see here. First of all, one more thing. Did anyone notice that I emailed you solutions to the problems we didn't do?
Yes.
I emailed you, all of you, right then after class. I went to my office. I finished filling out the entire packet for 2-1, all the problems that we didn't do, and I emailed it to you. Did all of you get that email from me? If you, so far I only see one person's hand raised. If you did not get an email from me last Wednesday with all the solutions to the rest of the problems from 2-1, you need to come see me about how to check your email in Canvas, because I'm sending you gold through Canvas email. I sent you all the solutions, and you could have had Wednesday, Thursday, Friday, Saturday, Sunday, Monday to look at all those solutions and learn from them. So please, I hope you're checking your Canvas email every day. If you didn't get that email from me, then come talk to me after class. Okay, so here we are, folks. We're on number 4. Everybody here? Now, again, everybody, you got to rotate your chair and face this way. All right, I'm going to start right here. So number 4, for each value below, enter the number correct to 4 decimal places. Suppose an arrow is shot upward on the moon with a velocity of 34 meters per second. The height after t seconds is given by h of t equals 34t minus 0.83. So there's our formula. Find the average velocity over the given time intervals. So average velocity, let's look at what this graph would look like. What we have is a parabola that goes through the origin, and it goes up, and then back down. And draw that picture, everybody. Draw that picture right there in your workspace. If you just draw it over to the right. This is a picture of an arrow being shot up on the moon. So as you imagine, on the moon, as you all know, the gravity is only 1/6 the value of the gravity here. So things kind of, they kind of like drift a little more on the moon, right? So you shoot up the arrow, and the arrow floats through the air for a very long time, and then it comes back down. So this is time equals 0. And then over here, I don't know how many seconds it takes for it to land. But I think what we're looking at is between 3 and 4 seconds. We're looking at the interval from 3 to 4. So keep in mind, when we write down the interval from 3 to 4, we're looking at a time interval. That's not a coordinate. Right? This has brackets, not parentheses. So this isn't a coordinate. That's an interval of time from 3 seconds to 4 seconds. So presumably, this is what we're looking at. right? So the arrow is here at 3 seconds, and now the arrow is here at 4 seconds. And we're wondering what's the average rate of change? That is the average velocity. Notice, folks, this is a distance versus time graph. So the slope represents a velocity. We're calculating the velocity of the arrow. How fast is the arrow going? And so if I draw that secant line, it's a secant line that's going through 2 points, we can use the slope formula and actually calculate the average rate of change of the arrow. So that's what we have so far. Now, what they're asking us to do is all those intervals from 3 to 4, from 3 to 3.5, from 3 to 3.1, and 3 to 3.01. Notice what's happening. If I go from 3 to 4, then I'm looking at that average rate of change. But if I bring this point closer to 3.5, now my 2 points are closer together, and my secant line is a slightly different slope. And those 2 points are coming together. If I now do the interval from 3 to 3.1, that's much closer. Now my 2 points are right on top of each other. And again, my secant slope is different from the original one. It's tilted up a little more. And then if I do the interval from 3 to 3.01, I'm looking at a really small interval from 3 to 3.01. And those 2 points are right on top of each other, almost right on top of each other. And the point of calculus is that if you bring those 2 points infinitely close to each other, then calculating the slope between 2 points is basically the same as calculating the slope at 1 point. And that's what we're trying to do, is we're trying to squeeze these 2 points closer and closer together. And that could give us the instantaneous velocity of the arrow at exactly 3 seconds. That's actually what we're interested in. How fast is the arrow going at the 3rd second? We don't know, but we can calculate the average velocity over shorter and shorter intervals, and that will approximate for us the instantaneous velocity of the arrow at time equals 3. Okay, so that's just setting up the problem. Now how are we going to do this? Everyone please draw another graph. Draw another graph just right below the other one. Same one, it's an upside down parabola. And let's look at our 2 values of an interval. We're looking at the interval from A to B. So it's just any given time interval, starting at time equals A, ending at time equals B. And if I go ahead and draw A and B on my graph, and I look straight up at where those coordinates are. Oh boy, you guys behind me might not be able to see that. I'm looking at finding the slope between those 2 points. In order to find slope, you need 2 points, and then you're going to use the slope formula. M equals y2 minus y1 over x2 minus x1. So what are those coordinates? What's this coordinate? And what's this coordinate? Let's do this coordinate first. What is it? Well, we're not looking at 3 and 4 anymore. We're looking at just some random A and some random B. So we know the x coordinate. What's the y coordinate? How tall is that right there? What's the height of that coordinate? F of A. That's the y coordinate. Remember, f of A represents the y coordinate. So if the x coordinate is A, the y coordinate is f of A. How about this coordinate? Oh, so I'm going to put that in. This is A, comma, f of A. That's the coordinate. So what about this other coordinate up here? The x coordinate is B. So what's the y coordinate?
F of B.
F of B. So that's going to be f of B, because remember, folks, f, the function always represents the y coordinate. So now that's f of B. So now what we can do is do the slope formula based on this information. I can call this x1, y1. I can call this x2, y2. And we can go ahead and do the slope formula where m equals y2 minus y1, x2 minus x1. And that, we're almost done creating a formula that we can use to quickly calculate all of those intervals without doing much work. So what is our formula going to be? What's the numerator going to be? What's my y2 minus y1? Aldo? What's my y2? And my y1? Great. And then what's my denominator going to be, Michelle? Yeah, just b minus a. Okay. Now, right now, you might be saying to yourself, Mr. G, you just wrote up a whole lot of things, and we haven't even done the problem yet. And that's true. We haven't started doing those individual problems yet. But I want you to see that we have now come up with a really handy formula, which we will use over and over again in this course, to calculate the slope between two random points. So I'm going to go ahead and start the first interval, 3 to 4. So now this is the actual problem on your paper. So if you want to go find 3 to 4 on your paper, we're going to show our work right next to that. Oh, we did it?
Yeah.
Thank you very much. Let's do 3 to 3.5. Actually, I'm going to show you 3 to 4 because even though we did do 3 to 4, we didn't use this formula. So I'm just going to show you how nice it's going to look. And in fact, can I see someone's work for who did do 3 to 4?
I don't know.
Thank you. Oh, did you guys all go home and finish the rest of these? Did we do all of them?
No.
Oh, okay. You finished all of them. Very nice. So what did we get for the 3 to 4? 28.19? Is that what everybody got? Okay, so watch now as we use the slope formula here. It simply becomes what? F of 4 minus f of 3 all over 4 minus 3. That's really quick and simple in terms of just writing down a formula that captures the slope of the secant line from 3 to 4. Now at that point, you'd still have to use your calculator. You'd have to take your calculator, plug 4 into the function, plug 3 into the function, subtract those two values, and then do 4 minus 3, and then you'd have your answer. But the point is, that's a quick and simple formula we can use to now do all of these. So folks, let's try it. How about the interval from 3 to 3.5? So the slope on that interval is going to be f of 3.5 minus f of 3 all over 3.5 minus 3. And at this point, you would all take out your calculators, your graphing calculators, preferably. I suppose you could use your phone calculators, but that won't be as convenient. And what you would do is you would take the 3.5 and plug it into the function. So this is my function. I'm going to do 34 times 3.5 minus 0.83 times 3.5 squared. And that gives me the first number, which is 108.8325. And now, here's the beauty. Now, I really do encourage all of you to have your calculators out. Because now that I typed in the expression once, I can hit second enter. And by hitting second enter, it pulls up the exact same expression that I just had. And all I have to do is go back and change my 3.5s into 3.0s. And that's me plugging in 3. It takes almost no extra time to type in that whole second expression and now give me the answer, 94.53. So I realize all of you might have a slightly different calculator, but one of the goals in this course is to learn how to be efficient and fast with your calculator. And so once you type the expression in once, you can just hit second enter, and then you just edit the expression you already put in. And of course the bottom is 1. Okay, now from there, I leave that to you. All of you can finish up that, which is just a matter of typing in those decimals and dividing by 0.5, and then you'll have the average rate of change, or the average velocity of the arrow over that interval. So what answer did you get? 108.325 minus 94.53 divided by 0.5. Did you get 28.605? We did not do this one before, right? This is a new one?
Yeah.
Okay, so I'm just gonna walk around real quick, just see everybody's progress. You've got everything typed in there. If you're already done with this one and you got 28.605, go ahead and do the next one. You're gonna set it up in the exact same way. You're gonna use this fancy formula that we just derived, f of b minus f of a, all over b minus a. Oh, you did it. You did right to formula. And in that way, you can just move on down the list and compute these relatively quickly. Nice. Hey, what can I show you? So once, you don't have to do the f of or the h of, you just have to type in 34, and then the first number we're typing in is 3.5. And then that's minus 0.83 times again 3.5. But that one is being squared. Where's the square button? Oh yeah, squared. There you go. So that's the first one. And you'll notice that you got the same thing I did, 108.83. Yeah. So now what you do is you hit second enter. Go ahead, second enter. And you'll see now that your cursor is right back on the same equation. So now you can change this 3.5 to the 3 point negative 2.
You know what that is? Yep, 3.0. So now you're at 3.0, and you move over here to 5. And also change that one. And now you have the second decimal. How did we go? Okay, you're already done, but you see the point. Does it work?
Now, looking around the room, I notice a lot of you already finished this problem just by crunching the numbers, and that's just fine. I'm glad that you had that experience. Ultimately, it is all just about, plugging numbers into your calculator. I think that's all that really has to be said about this problem. I'm not going to go through and compute all of these other intervals, but I will call on you to go ahead and tell me what you got for the other intervals.
I have a question. Are we gonna leave it as like
A decimal?
Yeah.
Yes.
Okay, so
Wait, was that really your question? I'm sorry, I didn't mean to cut you off.
I think so, yeah, because you don't want it as like a slope format. Is that what-
Correct. Okay, now see, this is interesting, folks. So far in this class, I've said that a slope is always a fraction, and therefore it should be over 1. However, in the context of this problem, they said find the average velocity of the arrow. And so how fast was the arrow going? 28.605 meters per second. That's how fast the arrow was going. Meters per second, it's not miles per hour, but it's still a velocity. And so in this context, you wouldn't say, you could say that. You could say 28.605 meters per 1 second. And then it would be a fraction. Or you can just say 28.6 meters per second. Both answers are fine. I guess I just asked you, if someone asked you how fast you drive to school, would you say 35 miles per hour? Or would you say 35 miles in 1 hour? What would be the most natural way to respond to someone? 35 miles per hour, or I drive 35 miles in 1 hour? Yeah, so it depends on context. That's a great question, Richard. Okay, so folks, could I have a volunteer give me the average velocity of the interval from 3 to 3.1? What did you get, Sela? Sorry?
I'm still working on it.
Oh, you're still working on it, okay. Somebody already has it, yes, Stephen?
28.937.
28.927.
No,
And-
937.
Oh, 937. And then somebody else who has the interval from 3 to 3.01? Allison?
I'm working on it.
Oh, you're still working on it, okay. Someone who already has it? 29.1? 01? 011? Okay. Oh, I'm sorry, 01. Oh, gotcha, 0.117. Okay, and then the interval from 3 to 3.001? Does anyone have that already? 29.1? 0192. Okay. So folks, what do you notice is happening to these numbers? As we make the interval smaller and smaller and smaller, what's happening to the velocity? It goes from 28.6 to 28.9 to 29.01 to 29.019. The numbers are, maybe you're all still crunching your numbers. You can all stop crunching numbers. You can always finish it later for homework. What's happening to these numbers?
Be more refined, I guess.
Yeah, they're getting more refined. The numbers are increasing. Are they going to keep increasing forever? Is this 29 going to eventually become 30 and then 31 and then 32? No, it's just getting more refined. Because after all, it's an arrow on a planet. When they originally shot the arrow, it was 34 meters per second. So once you fire an arrow, is that arrow going to speed up over time or slow down over time?
So
It's going to slow down over time. So this looks pretty reasonable. And the question at the very bottom of your page, what was it? What do you predict is the instantaneous velocity? So what do you think? Just as a prediction, how fast was the arrow going at time equals 3?
29.02.
Yeah, maybe 29.02. That's a very reasonable guess. So this is our first example of how calculus was invented by Newton and Leibniz in the late 1600s. They were wondering about instantaneous velocities. How do we know how fast something was going at a particular moment in time? And the only way to get at that information is to choose 2 times and bring those 2 times closer and closer and closer together. And if you can bring those 2 times infinitely close, the answer you get will essentially be the speed at that moment. Okay, any questions about that particular problem? I realize some of you are still plugging away, typing in numbers and that's satisfying to finish it. But I'm going to suggest let's all stop working on that one and move on. Let's take a look at number 6. Now, number 6, folks, what does that function look like? Does anyone know off the top of their head what the shape of that graph is? For instance, is it a straight line? No, it's not y equals mx plus b. It's not a straight line. Is it a parabola? No. So do any of us know what that graph looks like off the top of our head? No, none of us do. So what should we do? Before we begin the problem, what should we do? We should graph it. And that's always what we're going to do, folks. Before you begin any problem, you always want to take a look at what this graph actually looks like so you know in your head what you're looking at. So I'm going to go to Desmos, as I will often do, and type in the function 1 over x plus 12. Now there. Is that the graph you expected? Maybe it is, maybe it isn't. What prominent feature do we have right here at x equals negative 12? What is that called when a graph shoots up and gets closer and closer but never reaches the vertical line? And then it shoots down and gets closer and closer but never reaches. What do we call that line, that imaginary line at x equals negative 12? Somebody said it, it's an asymptote. That's an asymptote. So this is a rational function, 1 over x plus 12. There's an asymptote right there, and that's what the graph looks like. If you zoom out, you'll notice it's just basically a horizontal line with a little strange blip that happens right there at negative 12, an asymptote. Now, what are we asking for? Number 6, it says, given this function, find the average rate of change on the interval 2, 2 plus h. Well, we might all want to wonder, what is the interval 2, 2 plus h? You all understand the first part. Where should I go? To the number 2. So here's the number 2, right there. And then where's 2 plus h? What is h? It's just a variable. It could be anything. H could be 1, in which case 2 plus 1 is 3. And so the interval would be 2 to 3. The point is 2 plus h represents any point just to the right of 2. So everybody, let's begin by drawing a picture of our graph. So that's what the graph looks like. Everybody, let's turn around here and look at my picture I'm about to draw. I want you to draw the same one. Here's my graph. Here's 0. Here's 2. And here's 2 plus h. The point is 2 plus h is just a variable representation of some coordinate to the right of 2. Now what's our graph doing? Remember, it starts way over here at negative 12 with a vertical asymptote, and it comes down, and it's just basically meandering its way at a very slow descent off to that side of the graph. So are you drawing a horizontal line? No, it should be slowly descending. So what you all might want to do is exaggerate it a little bit. Even though it looks almost flat over there, exaggerate a little bit and make your graph look something like that, so that it's more obvious to you that it is actually decreasing over time. And that's the graph we're looking at. So everybody, let's start by getting a nice little picture that looks just like that. And let's go ahead and draw those coordinates. So, what's that coordinate? We know the x value is 2. What's the y value of that coordinate? What's any y coordinate? F of x. F of x. So we could go ahead and say that that y value right there is, are we talking about f? Yeah, we are talking about f. That y value is f of 2, right? So that coordinate right there is 2, f of 2. This is how we're going to be representing coordinates in general. Once you put in the x coordinate, the y coordinate is simply f of that number. So what's this coordinate? What's the x coordinate? Hold on a second. What was your name again? Josue, that's right. Josue, what's the x coordinate? What's the y coordinate? Yeah, f of 2 plus h. Okay. Does everyone have that? We're going to be drawing a lot of graphs, and the graph that I just drew up there is pretty standard in terms of what we'll be drawing and how much detail you really want to have on a graph. Oh, and keep in mind, where's my second y coordinate? Is it above f of 2 or is it below f of 2? It's below it because the graph is decreasing over time. Okay. So everyone has that graph? So what are we doing anyway? I don't even know if we finished reading the problem. You don't even have to read the problem until you're done getting a good graph. So, given f of x equals 1 over x plus 12, find the average rate of change of the function f of x on the interval from 2 to 2 plus h. Your answer will be an expression involving h. So, we simply want to find the slope again. Notice that since we have our two coordinates, we can just go ahead and call that x1, y1 and x2, y2. And we can go ahead and do what we just did in the last problem. So we can say slope in general is going to be f of b minus f of a all over b minus a, where a is the left endpoint of the interval and b is the right endpoint of the interval. This is a general formula that I hope we all memorize and become very comfortable with. This is the formula for the slope on interval a to b. Right? So I'm just reiterating that's the formula that we just came up with. So now we just plug everything in. So what's f of b in this case? I'm going to go around the room and call on some people. Aldo, what's my f of b in this case? Yeah, f of 2 plus h. And then what's my f of a in this case, Brendan? A is my first part of the interval, and I'm looking for the f of part. Yeah, well, f of 2. And you know what, folks? I'm sorry. Maybe I'm confusing things by referring back to a and b. You could just as easily be referring to y2 minus y1 right now and x2 minus x1. And maybe that's how I should have said it. I'm just going to say it just so everyone sees it. You can also just think of it as y2 minus y1, x2 minus x1. So in other words, who did the first one? Josue? So y2 was the f of 2 plus h. And then, going back to Brandon, what's our y1? Yeah, f of 2. And then, what's our x2, Julian?
2 plus h.
Yeah, 2 plus h. And then what's our x1? 2. Okay. Well, we're moving along here, folks. We're understanding how to write down a formula that's going to tell us the average rate of change over a certain interval. So now we just have to deal with this. So let's do the denominator first. That's wonderful. What nice thing happens in the denominator? The 2's cancel out. That's wonderful. So now it's just all over h. Now the top, we have a lot of work to do in the top. And I should go ahead and tell you now, calculus is a lot of algebraic simplification. When you do calculus, you do a lot of algebraic simplification. So first of all, what is f of 2 plus h? That means let's plug 2 plus h into the original function, which is what? The original function is 1 over x plus 12. So what am I plugging in for x?
2 plus h.
2 plus h. So the first part there is 1 over 2 plus h plus 12. Is that right? We're just plugging 2 plus h into the function that they gave us. And then the second part, minus f of 2, we're plugging 2 in for x. So the second part is going to be 1 over 2 plus 12. I realize we could have all already added the 2 plus the 12, but I want to make sure everybody sees what I'm doing. I plugged in the 2 plus h into the function, and I plugged in the 2 into the function. So now let's go ahead and add the 2's and the 12's, and we should all have an expression that looks like this. 1 over h plus 14 minus 1 over 14 all over h. There's some good news, bad news right here. They said, find the average rate of change on the interval 2 to 2 plus h. And it says your answer will be an expression involving h. Is that an answer involving h? It is. Okay, however, we're not allowed to leave h in the denominator. And here's the reason why. We're wondering what happens when I slide these 2 points infinitely close together. Well, how far apart are 2 points that are infinitely close together? H represents their distance apart. And how far apart are they if they're infinitely close? H, but if they're infinitely close, what's the distance between them?
Infinite.
Well, infinitely small. And what's a value that's infinitely small? It's essentially 0. Near 0. Very good. It's near 0, but it's essentially 0. And in this expression, am I allowed to plug in 0 for h? Like everybody try. If I plug in 0 for h right now, that's 0 plus 14 minus 1 over 14 all over 0. Regardless of what the numerator works out to be, am I allowed to divide by 0?
No.
I'm not allowed to. So this expression is not finished. We need to simplify this expression so there's no h in the denominator. And so this is going to involve a lot of algebraic manipulation, but it's a good trick that you should all know. So everybody, you'll probably need to drop down to the next line of work, and let's learn how to simplify an expression like this. We want to cancel the h from the denominator. In order to cancel the h from the denominator, what we would need is another h in the numerator, right? Wouldn't that be convenient? If we did have another h in the numerator, what could we do? We could just cancel them, and then there wouldn't be an h in the denominator anymore. Unfortunately, do we have an h in the numerator? We do not. So what we need to do is, since we have 2 fractions here that are being subtracted, we need to go ahead and subtract those 2 fractions and see what happens. So can we go ahead and subtract these fractions right now as they are? Why not?
They don't have the same.
Yeah, they don't have the same denominator. So we need to find a common denominator for these 2 fractions and then actually subtract. So what is the common denominator? Well, this denominator is h plus 14, and this denominator is 14. So how do we build a common denominator? Yeah, this fraction you multiply 14 top and bottom, and this fraction you multiply h plus 14 top and bottom. If that's not immediately obvious to you, let's do a simple example. If I wanted to add 1/2 plus 1/3, the common denominator would be 6. But the easy trick is I just take this fraction and multiply top and bottom by that denominator. And then I take this fraction and multiply top and bottom by that denominator. Is that fair? As a rule, that's how you find the common denominator. So that's what we're going to do here. For this fraction, I'm going to multiply top and bottom by that denominator. So that's 14 times 1, 14 times that. And then over here on this fraction, we're going to multiply by that denominator top and bottom. So it's going to be h plus 14, h plus 14. Now, folks, as we do this process right now, first of all, I hope everybody's writing. This is a lengthy computation. I hope you're writing this as we go. Don't just watch. You need to be writing it down. You might look at this and say, whoa, what's happening right now? Are we in calculus or are we in algebra? The fact is there's a lot of algebra that goes into a calculus course. There's a lot of algebraic manipulation that you have to do. This is exactly what Newton and Leibniz did when they were developing calculus. Okay, so now, folks, let's keep going. This fraction now is 14 over 14 times 14 plus h minus h plus 14 over 14 times 14 plus h, all over h. Do we have a common denominator? Yeah, we do. And now that we have a common denominator, we can actually subtract the numerator. So let's subtract the numerator. So now I have a common denominator on top, that's 14 times 14 plus h. And the top now is going to be 14 minus h plus 14. And all of that is over h. Now you might say, geez, this looks worse. I don't know where we're going. How is this going to cancel out the h? But now look at the numerator of your numerator. What happens when we do 14 minus h minus 14? What are we left with? 14 minus h minus 14. It's 14 minus h minus 14. What happens to the 14s? They cancel out, and we're left with just an h. So that numerator now is just h all over 14 times 14 plus h. All over h. This is a doozy of a problem. It's almost like hazing. Like you join a calculus class and you get hazed by doing some really beefy, meaty algebraic problems. Okay, so now what do we have, folks? We have this numerator being divided by h. And another way of writing that is dividing by h. That's h over 14 times 14 plus h. Divided by h over 1. Right, because this h is really h over 1. So we have that fraction being divided by h. And how do you divide by a fraction? You multiply by the reciprocal. So now we have h over 14 times 14 plus h times 1 over h. And now what do we get to do with the h's? Because there's one on top and there's one on bottom. We can actually cancel them. And we end up with 1 over 14 times 14 plus h. We can all exhale. That's the end of the problem. The question was, find the average rate of change on the interval 2, 2 plus h. And they said the answer would be an expression. Oh my gosh, it logged me out. It said it would be an expression involving h. And there it is. The expression is 1 over 14 times 14 plus h. That's the slope between any 2 points that start at 2 and a point to the right of 2. Yes?
I get this, but I don't get it when it comes to something being squared. Because then you have to do binomial factors or something like that.
Well, that's true. You'd have to like FOIL.
Right.
Yeah. When we get to a problem like that, we'll practice it. Okay, great. Simone, thanks for asking the question. Allison, you smiled and laughed. Was there a question I thought you had? No, not right now.
I'm just trying to finish.
Okay, fantastic. Yes? Oh, you're right. When you distributed the h, that was a negative h, wasn't it? Thank you for catching that. Yeah, maybe a couple of other of you caught that as well. That should have been a negative h, and therefore that's a negative h. And then when you canceled out the negative h's, those are negative 1. You're absolutely correct. The answer is negative. Thank you for catching that. Steven.
Here, a question. So that towards the end, where they're over the h, the bottom h, where does that h disappear to?
Well, because I'm saying that this fraction is being divided by h, so I just rewrote it as that fraction being divided by h.
Okay.
Because that way, division by a fraction is the same as multiplication by the reciprocal.
Okay.
Yeah. Yep. Okay. Well, so folks, for that particular problem, the final answer is negative 1 over 14 times 14 plus h. Now, we should at least spend a moment to look at that answer. What on earth does that answer mean? Let's choose a nice and easy one for h. Let's say h equals 1. We're saying an interval that's 1 second long. Therefore, we're looking at the two values, 2 plus h, which is really 2 plus 1, which is 3. So we're looking at the time interval from 2 to 3, and we're wondering what that slope is. What's the slope between 2 and 3? So now that I'm saying h is 1, I just take my formula, negative 1 over 14 times 14 plus h, and I plug 1 in for h. That's negative 1 over 14 times 14 plus 1 is 15. And does anyone know what 14 times 15 is off the top of their head? 210. And so that is the slope. The slope from that point to that point is negative 1 over 210, which you would read as saying down 1, right 210. Down 1, right 210. This is a very, very shallow slope. Just imagine you're going down 1, and then you're going right 210 units. So that's incredibly shallow. And that's what the formula just told us. Now, if you pick any value of h that is determining however close you want those 2 points to be, you now know the slope between the 2 points. And here's the most powerful part. What if I wanted to choose 2 points that were infinitely close together? What if I brought this point infinitely close what would my h value be if the 2 points are infinitely close? The h value is 0. And can I plug 0 into this equation?
Yes.
Yeah, -1 over 14 times 14 plus 0. That's -1 over 14 times 14, which is 196. That just gave us the instantaneous slope at that point. Now I know exactly that the slope right there is precisely down 1, right 196. And that right there was the invention of calculus by Newton and Leibniz in the late 1600s. The ability to slide 2 points infinitely close together to find out what the slope is at 1 point rather than the slope between 2 points. Okay, we'll reiterate that message over and over throughout class. My phone just went off, so that means we get to take a break. Let me just verify where we are. I think, oh yeah, we just have a couple more questions from this section, which are actually very fast compared to the 2 we just did. And then we'll start 2-2. So everybody, let's take our break. The time is 11:51. Let's be back here at 12:01. Everyone be back in the room at 12:01. So you were asking about how to do it with a square term?
Yeah,
We'll do that together.
okay,
Yeah, we'll do that in class. I don't think you'd have a homework problem with that.
yes.
In what section?
2.1, I think that's what I saw there.
Really?
Or
Is-
maybe, but I do watch the, is that one, isn't that one? Okay.
Yes, this is like one we did do. We did this one, it's on, I think, page 1 or 2.
Oh, okay,
So you can look back at your notes,
Mhm.
or yeah, you can come in office hours and we'll do another one.
okay, great.
Okay, you're welcome. Yeah. Oh, like how was I choosing H values? Well, first of all, the answer is this one. That's the answer. And I was just showing you what it means to plug in a value. So I just randomly chose the value number 1 because I wanted to say what if my 2 points were 1, meaning 2 and 3. So I just arbitrarily chose h. You could choose any h value. You could choose the h value of 10. Because then you'd be looking at 2 and 2 times 12. So you'd be looking at 2 and 12. And then that would be good. And in that case, you just plug in h equals 10. It's going to tell you the slope between this coordinate at 2 and the other coordinate at 12. Does that make sense? Yeah, so that's the actual answer that you would type in the system. And this is just me showing an example of what you do. And the best part is that you can also plug in h equals 0. That's the most important thing. That you plug in h equals 0. Those 2 points are actually right on top of each other, and that gives you the instantaneous tangent slope instead of a sequence slope. Okay.
Stephen,
Yes,
I said that I emailed out notes to everyone. Did you in fact get those notes?
I did.
Through email?
Yes. Do you want me to show you?
Did I just? Yeah, please do. Because now I'm looking back through my email. I can't find my sent email. I'm feeling crazy like I didn't actually send it to you guys.
You did, I saw it.
You did? I can't find my sent. Thank you, Simone. mat213. Oh, I did send it.
Did you find it?
Okay, I found it. Yeah, I did send it. Whew, boy, I was gonna feel really bad.
So you want to give us another week to do the homework?
Yeah, you have until next Monday to turn in 2-1.
Okay. Okay, folks. Okay. Folks, Brendan, and although we're walking up, I'm going to go ahead and get started. So, okay.
Yeah.
Okay, folks. Now, that last problem was a doozy. And I think that's, one reason why calculus gets a rap for being tricky, is because some of the problems are quite long. But I just want to show you real quick. Here we go. I do want to show you that I did in fact send you the notes. Even though now I can't find it. I cannot find it. Oh, this is so sad. Well, check your email, folks. I really did send you the rest of the notes. And the most important thing, oh, here we go. I just sent it again. So, whether you find the original email or the one I just sent, here are the notes from section 2.1, sorry. And I want you to see that, let's just say that your first time through that problem, you're like, oh, that was a little rough. Then you can go ahead and open up the notes that I just emailed, and you can look at them again, fresh. So here's the problem we just did. There we go. Okay, there's the one from this morning that we did first, and now here's the one that we just did. And importantly, you can take a look at everything fresh. So there again is that graph that we just drew of the function decreasing over time. My two coordinates that exist at those 2 points, us plugging all of that in, simplifying your fraction using a common denominator, and then canceling out the h and finishing the problem. So if that's helpful to you to go back and look at it again on a separate sheet of paper, then I really encourage you to get that out of your email so you can look through it. Okay, close. Sure. Oh, and I just closed mine. Okay, any questions before we get started or keep going? Okay, then just look at the very next problem. The very next problem is what, number 7? Okay. Fortunately, these next few problems are very simple and simply conceptual. This one says, here's a graph of f of x. Estimate the values where f of x has a horizontal tangent. So a horizontal tangent just means that the slope, your slope indicator, is flat. So where is the horizontal tangent? There's one. It's just the top, it's just the maximum value of a hump in the graph. So there's a horizontal tangent. And what's the x value for that horizontal tangent? -5. That's it. So they're just saying when x is -5, the graph has a horizontal tangent. And then you move along the graph, and then you get to here, and there's another horizontal tangent, meaning that the slope is 0. A horizontal tangent means the slope is 0. And what's the x value for that horizontal tangency? 6. That's it. The answer to that problem is -5 and 6 are two x values where the graph has a slope of 0, meaning that your little slope indicator went horizontal. Because right here, my slope indicator has a positive slope, now a 0 slope, now a negative slope, now a 0 slope, now a positive slope. So that's it. That's the whole problem. You just type in the answer, -5, 6. Same thing goes for number 8, 9, and 10 here. Consider the graph below. What is the sign of the slope of the tangent line at that point? So right here, what is the sign of the slope? Positive, negative, or 0? Negative. What is the sign of this slope? Positive, negative, or 0? Positive. Positive. And how about the last one? Use the graph of f of x to estimate the slope at x equals 2. So at x equals 2, what do you think the slope is? First of all, is it positive, negative, or 0? Negative, because it's pointing downward. Okay, so we know it's a negative slope. Well, how steep is it? I would recommend, and I told this to one of you who emailed me, I would hold a sheet of paper up to your computer screen and actually draw a line, a long line that appears tangent to that point. If I had a ruler, I would hold it up against it, but the key is, I'll just use my pen here again. I'm looking at that slope, and to me, it looks to me like that slope is down 2, right 1. What do you folks think? Just looking at my marker right now, my marker is going down 2 boxes, right 1 box. And I'm thinking that's pretty close to what the real answer is going to be. If I come up here, I still think it's down 2, right 1. And in fact, just to demonstrate that one to you folks, that you're just eyeballing it, you're approximating what that slope is. If I go on back over here more, and I go to that problem, here it is. Estimate the slope at x equals 1. Well, right here at x equals 1, this is a different problem, but it appears to be fairly, actually, I would say that's about down 1, right 1. I'm just looking at, I use my marker here. I'm looking at the slope when x equals 1, so right there. So what do you folks think? Do you think that's down 1, right 1, down 1, right 1? I mean, it's pretty close. It is just an approximation, but I'm going to go ahead and try it. I think the slope is approximately -1/1. Down 1, right 1. And they gave me credit for it. So it's really just an eyeballed, rough approximation of what that slope is. Okay, whew. That's 2.1. So, wrapping up 2.1, folks, I hope that you've already gone in
to section 2.1 and watched all the videos. It's helpful to see it again. It's helpful to see it twice. In fact, can I just tell you a quick story? I think I told you I'm in the math class right now. The class is called Group Theory. And I was reading my homework over the weekend. I was reading section 1.3 in the textbook. Section 1.3 was about 5 pages long. I read those 5 pages, and at the end of it, I didn't understand a single thing the text had said. Really, truly. I was like, oh my gosh, I don't understand any of this. So then what did I do? I read it again. And the next time I read it, it was all so obvious and easy. And it was like mentally in such a flip-flop. Like the first time I read it, it looked impossible. I considered dropping the course. I was like, whoa, this looks crazy. But then all I did was read it again, and I was like, oh, okay, that's very reasonable. That makes sense. Okay? So I share that story with you in all humility, that that's what the process of learning is like. Sometimes the first look at it, you're like, whoa, that's confusing. But then the second look makes a lot more sense. And so that's why I really recommend you watch these videos and you read the textbook. Because normally it takes 1 or 2, normally it takes 2 or 3, that's what I should have said. Normally it takes 2 or 3 exposures in order to really understand something. Okay, folks, let's do it. Let's move on to 2.2. 2.2 is one main idea. In fact, the title of your notes for section 2.2 is called Limits and Continuity. So the first concept we're going to talk about is a limit. And you might want to write this down at the top of your paper or paraphrase it. When we talk about a limit in this class, we mean the y value is getting very close to something, but not actually getting there. So the word limit, we mean, what is the y value close to? And that's probably the big key question. When we take a limit, we're saying, what is the y value close to? So here's just a quick example. In this little graph that I have right here, I have a function, and I'm looking at a particular x value of c. And so if I'm just looking at the x value of c, and I look at this graph, I'm not actually looking at the point that's there. I'm just saying, what is it getting close to? And the function is, in fact, getting close to this y value L. So we're just saying, what is the y value getting close to? And what we're often going to do is use our 2 pointer fingers and ride the graph towards a particular point and check to see that our fingers are touching. And wherever they're touching, that's the limit. Let's do a concrete example. Let's do a concrete example. The very first one on your page. So number 1. Does everybody have that? I should look at the packet that you have in front of you because did everyone get one? I have a lot of extra photocopies up here. Everyone has the one that says 2.2 up at the top? Okay. So in our first example here, let's take a look. There's 4 distinct problems that are all about this graph. First of all, what do you think of this graph? It's kind of an unfortunate looking graph. We don't often look at graphs like this. Normally we look at a straight line or a parabola, something nice. This one is not particularly continuous, is it? The graph is moving along, it stops, it jumps down here, and then it stops, and it comes back up here, and it moves along. So it's a pretty bumpy ride. We would say this is not a continuous graph. It's not continuous because if you're tracing it with your pencil, you'd be moving along, stopping, putting a dot right here, and then coming back up here, and then moving along. So we call that discontinuous if you have to pick up your pencil to trace the graph. A parabola, you can trace that graph without picking up your pencil. A straight line, you can trace that graph without picking up your pencil. A discontinuous graph, you have to pick up your pencil and move it around a lot. So this is very discontinuous. So let's take a look at what these problems are asking. Here it says, find the limit as x approaches -1, and then you'll notice there's a little negative sign to the upper right of the number. That means from the left. So this says, find the limit as x approaches -1 from the left. So everybody take your left finger, use it as a pointer, move along the graph as we're approaching -1, and as we approach -1, what y value are we getting close to? Not -1, the positive one. Yeah, we're always going to ask about the y values. Yeah, the y value. So if we take the limit as we approach -1 on the x-axis from the left, then the y value is approaching 1. So everybody go ahead and write equals 1. That first answer is 1. I'm going to do some examples with you. All right. Now this problem says find the limit as x approaches -1. So we're still approaching -1, but this time we're approaching it from the right. That's what that little plus sign to the right of the 1 means. So now take your right hand finger and you're going to ride along the graph and you're moving towards x equals -1. And as you get almost to -1, what's your y value? 2. So that one is equal to 2. So the first one was equal to 1. Your left finger was approaching the y value 1. This one, the answer is 2 because your right finger is approaching the y value 2. Now this question, you'll notice it just says, what's the limit as x approaches -1? There is no little tiny plus or minus sign right there. And what that means is they want you to take both fingers simultaneously and tell me, are you approaching the same value? We are not approaching the same value. There is no single number that our left and right finger are both approaching. And therefore, this one you'd write DNE, does not exist. DNE. DNE is a phrase that we'll use fairly often. It just means does not exist. So that particular limit, DNE, does not exist. What that tells us is that at that point, the graph is discontinuous. That if you were tracing it with your finger, you would have to pick up your pencil and put your pencil back down again in order to trace that graph. Okay, so far we had the left-hand limit was 1, the right-hand limit was 2. The general limit does not exist because your fingers are not approaching the same y value. And then finally, oh, that should say, what's f of -1? So what is the actual function value at -1? And remember, okay, I'm so sorry, folks. Write in f of -1. I don't know where the f went. F of -1. What again does f of x represent? The y coordinate or the height? What is the actual y coordinate of this function at -1? It's actually -2. The actual value on the graph for this function is -2. If you plugged -1 into this function, the value that it would give you is the number 2. So that last one is actually, I'm sorry, not 2. That's -2. Sorry, folks, that's -2. So this last one, f of -1 is equal to -2. Overall, this graph is pretty messed up because as we're approaching the x value of -1, from the left we're approaching the number 1, from the right we're approaching the number 2, and yet when you actually plug -1 into this function, you get -2. So this is an incredibly discontinuous graph. You actually look for what point exists on the vertical line at -1. Like what's the actual function value? There's a point right there. Because you'll notice these two circles are open circles. Just like when you shade a number line, an open circle means not included, and a shaded circle means included. That's the actual value of the function. All right, so let's try that again on number 2. I realize this is kind of low. For anyone in the room, you might have to stand up to look up here at the board. The second one says, find the limit as x approaches 2. So now we're all going to be looking at the x value of 2. What's the limit as you approach 2 from the left? So again, you would use your finger, move along the graph, and what y value are you approaching? -2. So the limit from the left is -2. So what about the next question? Find the limit as x approaches 2 from the right. So now you would take your right hand finger, and you would move along the graph, approaching x equals 2, and what value are you approaching now? Still -2. So that limit is also -2. The third question is, what's the limit as x approaches 2 from both directions? So now you'd use both fingers, because it's just x approaches 2. There's no plus or minus to the right of it. So now you would take both fingers and approach x equals 2, and what value are your fingers both heading towards? -2. So this is good so far. This is what we would expect from a continuous graph. That for any given x value, our fingers are pointing towards the same value. That means there's no jump in the graph. So far, this looks like a continuous graph, that you could trace it with your finger. Unfortunately, the actual value of the function at x equals 2 is not -2. The actual value of the function at 2 is -3. And that's the last question. What's f of 2? F of 2 means you go to the input value of 2 and you look for the dot on that vertical stripe, and the dot is at -3. So even this is a discontinuous graph, meaning if you were trying to trace this with your pencil, you'd be drawing, 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 stop, make a little dot, pick it back up, and then draw, draw, draw. So as we talk about limits, we're trying to develop this notion of what does it mean for a graph to be continuous. The friendly definition of continuous means that you can trace the whole graph without ever picking up your pencil. And so far what we've seen is there are 2 times you have to pick up your pencil. And I'm going to draw it. There are 2 times that you might have to pick up your pencil. One is if the graph simply stops and then jumps and moves along its merry way. So that would be discontinuous, meaning that the graph literally jumps from one spot to the next. And that's called a jump. Hop. That's what it's called. Or the graph could be discontinuous because you're moving along and there's just a gap. There's just a hole. It's just missing a point. There is no point there. Or it could be that that single point is just located somewhere else. So these are 2 types of discontinuities in a function. Now, right now, you might be asking yourself, what are we even talking about right now? We're talking about graphs that are continuous versus discontinuous? Yes. We're talking about when are we able to mathematically say that a function is continuous? That's nice and continuous. I can trace it with my pencil without ever picking it up. Versus when is a graph not continuous? And a graph is not continuous if there's a jump or a gap. That's very obvious in English. You know, you can just look at it and say, that's continuous, that isn't. The problem in calculus is how do we make that mathematically precise? How could we just look at a function without looking at the graph and know whether or not it's continuous or discontinuous? Okay, so let's take a look at number 3. Would you call that a continuous graph?
No.
No, it's incredibly discontinuous. It jumps around all over the place. You got points all over the place. This is a very discontinuous graph. We know that because we're looking at the graph. But if we were a species of aliens in the galaxy and we didn't have eyeballs and all we had was a function f of x, how would we know if the function was continuous or not? How would you know if a function was continuous or discontinuous if all you did was look at the equation and not look at the graph? That's what we're trying to get at. Okay, so let's try this again. What's the value of f of 1? Meaning when you plug 1 in for x in the input, what's the output? Where's the actual output?
Is it 1 and 4? Or is it?
Well, those are open circles, so it's not an output. There is no output for x equals 1. Literally, if you went to this function and plugged in 1 in your calculator, it would probably be an error message saying, sorry, you can't compute that value. So for this particular one, when you look vertically above the x value of 1, and you don't see any shaded point, there is no value. So right there you can put DNE. Does not exist. There is no output if you plug in 1, because there's no point. Whereas, just to give you another example, folks, write down f of 3 right below it. Write down f of 3 right below it. What's f of 3? What's the actual function value when you plug in 3 on the x-axis? 2, because there's a dot there. That's telling you that was the output value when you plug in 2, or when you plug in 3. Whereas when you plugged in 1, there was no dot, meaning there was no output. Yeah, so we're just going to put DNE does not exist. Okay, so the next one. Again, how do we read this? The limit as x approaches 8 from the left. So let's find 8. There it is. And I'm going to use my left hand to approach the x value of 8 from the left. And what value am I approaching? 5. 5. So that's it. That's the answer. The limit, that is the limit of the y value as you approach 8 from the left, is the y value of 5. How about the next one? The limit as x approaches 7, so here's 7, but we're approaching it from the right. So I'm going to take my right hand, I'm going to approach the x value of 7 from the right, and what am I approaching? 6. There's no actual point there, but I'm still approaching 6. That's the point of talking about limits, is even if there's not a point there, we can all agree that we were actually approaching the y value of 6, even though it's not actually there. It was still approaching 6. Of f of 1? This one's not a limit. They're actually asking us what's the input-output value. Yeah, there's no limit there. This is just saying what's the actual output value. Thank you, Bob. Good question. Okay, and then finally this one, x approaches 4 from both directions with both fingers. So I'm going to approach 4. Here's 4. I'm approaching 4 from the left. I'm approaching 4 from the right. What value am I approaching? 2 different values. So because my fingers are not touching each other, there is no one value that I'm approaching. So again, that one is DNE, does not exist. The only time a limit, a general limit from both the right and the left exists is if your fingers actually approach each other. Okay, so that's looking at the graph. And as I said, this is just a straightforward matter since we have eyeballs. And we can just look at the graph and we can see if there's a point or not, or if they're approaching the same number or not. But the real goal is to just look at an equation and find out what the limit is without necessarily looking at the graph. But let's go ahead and look at the graph anyway. Let's look at this function. I'm going to type it into Desmos. And when you're at home, I encourage you also to be typing things into Desmos so you can see what they look like. So this is x squared plus 5x plus 6, all divided by x plus 3. Okay, so folks, what does that graph look like? Yeah, it looks like a linear equation. It looks like a straight line. Does it look continuous to you? Does it look like you can trace your pencil along it without picking it up? No. Now, see, this is where a visual is very misleading. Because what are we trying to do the limit of? The limit as x approaches -3. Let's zoom in on the graph. There's -3 right there. And let's look at the point. Oh. Do you see what's actually there at -3? It's actually a hole. It's undefined, there's a hole. So there is no actual point right there at 3. Even though from far away it looked like it was continuous. In fact, we just didn't know yet that there was a really, really, really small hole there. Now, how on earth would I have ever known that there was a hole right there, but not anywhere else? That's part of what we want to know, is how do we find holes when it's not obvious that there's a hole there?
Doesn't x plus 3 and the denominator is asking?
Right, very good. So let's look at this function together, folks, and just kind of consider, and we're going to turn around and look at the back wall here so I can write this down. Let's start thinking, how can I figure out if a function is continuous or discontinuous? You know, what can we do? So first of all, in this particular function, it's the limit as x approaches -3 of x squared plus 5x plus 6 all over x plus 3. So, yeah, there we have it. If we wanted to be approximate about it, we could just plug -3 in, right? Like, I think we all just saw the graph look something like this. And I can always just go to -3. And if I just plugged in -3, then provided there's actually a point there, if I plug -3 in, it'll just tell me what the limit is, provided there's actually a point there. So the first thought would be just plug -3 into the function. And whatever it equals, that's what the limit equals. Because if you're looking at a continuous function, the limit should be equal to the actual points that's there. So go ahead, everybody. At first pass, the first thing you do is just plug -3 into this function and see what it equals. So let's do it. That'd be -3 squared plus 5 times -3 plus 6 all over -3 plus 3. And what does that give us? 9 minus 15 plus 6 all over 0, which is actually 0 over 0. So that's decidedly unhelpful. And that's actually how we know that there's a hole there. Because on your calculator, what's 0 divided by 0? What's 0 divided by 0 on your calculator? Undefined. And remember a second ago, what did the graph show us at the point -3? What did the coordinate actually say? Everyone look. Wait. There we go. What does it say? -3 comma undefined. Because there is no value if you just plug in -3. If you plug -3 to that expression, you get nothing. It's undefined. So since plugging -3 to that expression doesn't tell us what point is actually there, we need another way of figuring out what the limit is. What value are we approaching from the left and the right? So again, you can do that visually, but there's another way. So now that we all see that you can't just plug in the -3, here's what you actually do. And again, this is where all the algebra comes in. Calculus is just a lot of algebra. What we have to do is factor the numerator so that we can cancel the x plus 3. Just like we had to cancel the h in that previous computation, we need to be able to cancel the x plus 3 on bottom with an x plus 3 on top. We do not have an x plus 3 on top, but can we factor this?
Yes.
Yeah, how does that factor? What does x squared plus 5x plus 6 factor into? And let's just review for everybody, because maybe it's been a while since you've factored. X squared plus 5x plus 6. You ask the question, what do you multiply to get 6 that adds to make 5?
X plus 2x plus.
Yeah, 2 and 3. If you look at a factor table for 6, you can multiply 1 times 6 or 2 times 3. So what can you multiply to make 6 that adds to make 5? The 2 and the 3. So we factor the top into x plus 2, x plus 3. And now what can we do? Now we can actually eliminate the x plus 3 and the x plus 3, and that leaves us with simply x plus 2. Now that we have simplified that expression, now we can, oops, sorry, we still need to write the limit as x approaches -3 of x plus 2. Now we can actually do this problem by just plugging in the -3. What happens now if we plug in -3? What do we get? We just get -1, right? And everybody take a look at the graph that's still on the screen. What does our graph actually approach if we look at -3? What are we approaching?
-1.
-1. So when we're looking at a function and you want to know a limit, the first thing you would try to do is just plug in the value. Because if you can just plug that in, it will tell you the limit right away. But if you plug it in and it's undefined, you have to do some simplification and cancel the denominator. Because almost always dividing by 0 is the problem. So by canceling the denominator, you're able to find the actual limit that you would otherwise have found by just looking at a graph. Let's try that again. Number 5? What does number 5 say? I can't see.
X squared plus x minus 30
X squared plus x minus 30.
over x minus 5.
And we're approaching
5.
Is it the limit as x approaches 5?
Yes.
Okay. So folks, again, we're saying, let's consider this function, which, if you graph the function, first of all, does anyone know what that graph looks like? It's not obvious what that graph looks like, is it?